of Calico Rock. I'll turn it sideways so you can see it better. Calico Rock. So this is in Arkansas. It's beautiful. Um, the weather today really reminds me of the day we went and visited this place because it was kind of gloomy. It was cool for sure. And this overlooks the White River. So anybody likes to go trout fish or fish, I don't know what kind of fish are in the river, but they a lot of times will go to the White River. And Calico Rock, it's probably 2.5 hours north-ish of here, up towards like Mountain View, if you guys know where Mountain View is. And it's just a small little teeny tiny town. There's a railroad that passes through it. But it has this huge rock structure that kind of juts out over the river, and you can just drive straight up to it. So sadly, this is really not a hiking venue because you can pretty much drive there, but you can go stand. You can literally go stand right here on the rock and overlook the river. It's beautiful. And so we like to go visit here. I'll tell you, if you go visit in the fall, you need to be aware of one thing. You need to be aware that it is tarantula mating season in Calico Rock. Okay. And to prove my point, every time we've gone, we run into a tarantula. And I hate spiders. I will not get near them. I'm the one taking this photo and I'm way zoomed in. So these were my friends and my husband decided to get as close as they could to it. And I said, no, thanks. So I'm going to zoom in so that you can all see. Do they bite? I don't know. I don't sit around and think about or talk about tarantulas, and except for when I show this photo. I just know that we've seen them every time we go, and so I don't know if they bite or not. You can choose to find out. Are you asking because you want to pick it up in your hand, Brennan? Are you that person who would hold a spider in your hand, no fear? I don't know if I could do that. I could not actually. So, anyways, just be aware of that if you decide to go to Calico Rock. But it is a beautiful place and it's worth the trip. Just keep your eyes open the whole time. Okay, we're going to get into. Yes, they are interesting. I cannot hold one. We're going to get into a little bit more about chemical reactions, but we're going to start to understand them from an energy standpoint. I'm going to give you a warning. This is probably some of the most technical stuff, besides maybe chapter 10, that we're going to get into with our course. So I consider chapter 7 to be the hardest chapter. Here's why. It kind of has the most stuff. There are 6 major topics we are going to discuss in chapter 7. And usually we cover a chapter in 2 lecture periods. We're going to take 3 whole lecture periods to get through chapter 7. So be patient with yourself. Make sure you know the tutoring info if you need to reach out to tutors during this time, or me, and help one another out as well in the group me with assignments through this chapter, because I consider it to be some of the toughest material we cover all semester. Okay. All right. So I'm showing you pictures right here. I want to talk about these pictures for a second as a way to leeway understanding chemical reactions and energy. Anybody know what this is a picture of? Any guesses? Obviously something bad happened here. There used to be a nuclear reactor in this location. Yes, Jenna, you knew, Chernobyl. So in Russia, back in like, I don't even remember, the 1980s maybe, they had a massive nuclear reactor here. Starting in like the 1940s and 1950s, nuclear energy was kind of up and coming. They started designing nuclear reactors. We started using these to create energy to do all kinds of things, power cities, so on and so forth. But nuclear energy is also very dangerous, okay, because it can release nuclear radiation, and that's very harmful to us. And so what happened is something went wrong in one of the reactors and it literally blew out of the ground. And everybody had to evacuate the entire city because of the amount of radiation that was released. All that to say, that's an example of what energy can do, okay? Over here, you see another type of chemical reaction, and a lot of heat is being released with that chemical reaction. And now we know heat can be released. We know temperature changes are a sign of a chemical change. We learned that like week 1, of course. But here's just a very dramatic one, right? A lot of heat, fire flames being released with that chemical reaction. And these are ways that demonstrate that energy is always at play when chemical reactions are going on, okay? So speaking of energy, I would like to ask you guys, help me think of some of the main forms of energy that we deal with. Anybody? There should be, I bet we could come up with a list of maybe 6 or so. What are some of the main forms of energy? Think about the different kinds of energy we interact with. Solar. Oh, Caitlin's got like all of them for us. So we've got solar, I'm going to also say ELEC, electromagnetic. Okay, solar energy, energy from the sun, it is electromagnetic energy. In a chemistry class, we tend to use the word electromagnetic more than solar, but they're the same thing. Caitlin said kinetic. We're actually going to get to kinetic energy, kinetic and potential in just a minute. So I'm going to leave that one off the list, although it's an umbrella type. We can group the kinds we're going to name here under kinetic and potential. Okay, Susanna said chemical. Okay, Caitlin said heat. The word I'm going to use here is thermal. Thermal energy. Okay, so we have solar, chemical, thermal. Susanna said electrical. Electrical energy. That's good. That's about 4. We just talked about one right up here with that explosion. What kind of energy did we say that was associated with? I'm watching the chat. Nuclear. That's right. That's its own form of energy. Can anybody think of another kind? Got some pictures here. Over here, these are nuclear. That's a nuclear plant with the big smokestacks. Chemical energy. Okay, Susanna said mechanical. Susanna, do you have the slides that I did not edit? No, you just are on it. You're on your forms of energy. Okay, so this is a pretty good list. All right, mechanical, nuclear, electrical, thermal, chemical. These are all different kinds of energy, and we are actually going to talk about kinetic and potential in a little while as well. Now, if we're talking about the human body, because you guys want to be health professionals, and a lot of times you are going to be dealing with all aspects of the human body in different ways. What kind of energy does our body use? You can actually pick from this list. I'm seeing some different answers. Chemical, thermal, thermal. Okay, these are chemical and thermal are the two related, but what do we feed our body? We feed it food. What kind of energy or fuel is in that food? It's certainly chemical, okay? Whoops, chemical. Okay. Food it contains chemical bonds. Food is chemicals, right? Natural mostly, unless you're eating, the genetically modified stuff. But chemical energy, that is what we feed our bodies. Now, our bodies take that food. We often call it fuel, right? In fact, I put this little picture of this Sports Endurance Nutrition magazine because it said fuel your body, right? So that's the way we think of chemical energy is fuel for our body. So how does that body take the fuel we feed it and generate energy? Anybody know the processes that do that for us? There's actually 2 we could name. When we feed it food, what do we then do to extract energy from that food? How do we get the chemical energy? Well, what begins to happen to your food after you eat it? Break down glucose into ATP, okay? The overall name for that, yes, metabolize, okay? So metabolism, this is the process in which our bodies break. It's the breaking down of chemical energy. And we take that chemical energy, we break down the food, we get the chemical energy, and then we use it for all kinds of stuff, whatever the cells need it for. It's distributed across the body. And a bunch of people earlier were saying thermal energy, thermal energy. Thermal energy is associated with the body. In fact, we are one walking, talking, giant exothermic reaction. Okay, do you feel warm right now? Does your forehead feel warm? Everybody, touch your forehead. Does it feel warm? Usually, right? Does it feel warm to you? Yeah, your body is exuding heat at all times. So we do exude thermal energy, okay? But the process for getting this chemical energy is called metabolism. Respiration is another way we extract energy, okay? This is extracting energy from oxygen. Okay, obviously we breathe in oxygen, we breathe out CO2, and that process as well allows our body to acquire energy from those things. So respiration and metabolism are two ways that our bodies take the fuel that we give it, oxygen and food, and acquire energy. Okay, and then we give off heat. All right. So I told you too before we really get into the nuts and bolts of chapter 7 that we were going to briefly talk about kinetic and potential energy. So what is kinetic and potential energy? How are they different? First off, what is kinetic energy? How could we just very simply define this? Anything that moves, energy of movement, stored energy. Okay, I agree with 2 of those. Aaliyah, I think you're already ahead of us. You're already talking about potential energy, okay? So we'll come back to Aaliyah's definition in just a second, but kinetic energy is the energy of motion or movement, okay? Anything that is moving, falling, whatever, has kinetic energy, all right? Potential energy is just as Aaliyah said, it is stored energy. Oops. Stored energy, okay? So kinetic energy, energy of motion, and energy can move back and forth between these 2 things. If you have an apple hanging on a tree, high up above the ground, that apple has potential energy, okay? And then if it falls, if it breaks off the limb and starts falling, now it has kinetic energy. So energy, kinetic and potential, can be transferred back and forth between the 2 forms, okay? So keep that in mind. Mostly today, I want you to know that we are going to focus on potential energy and how potential energy is stored in chemicals, okay, in bonds. So there is potential energy. I'm going to write this down. I'm going to start abbreviating energy, capital E, is stored in chemical bonds. All right. And we'll talk about how it's released and how it's made as you break or as you form chemical bonds. Another thing that we're going to do today that I want to just give you a heads up on, since we're talking about energy, we are going to start writing energy into chemical equations as though it's a reactant or product. Okay, so there might be times where you see me write energy plus, a reactant forms our product. Okay. Sometimes you might see me write energy in as a reactant. Other times you might see me write the reactants give off energy after they react, okay? If you get certain products, and then you might form energy on this side as well. All right, so energy can be written into chemical equations as a reactant, that's number 1, or as a product, depending on what kind of reaction it is. So just be familiar with this kind of terminology and get comfortable with these ideas. I think they'll help you digest and process what we're about to talk about. So we talked about energy. How do we know, I'm going to ask you this kind of overarching question right here. How do we know if a chemical reaction will occur? So to illustrate this point, I want you to look at the chemical reaction I have on this slide right here. Look at it, think about it. Anybody know what AU is? It is gold, okay? So we have gold and water. And we can perfectly write this viable chemical reaction that gold and water come together and give us gold oxide and hydrogen. All right, it's already balanced for you. But I want you to think about that. If I had a gold ring and I dropped it into a cup of water, is anything going to happen right before our eyes? Is that gold going to magically... Think about it. Just because you can write a balanced chemical reaction does not mean that you're automatically going to see the reaction happen, that the reaction is, I'm going to use the word favorable, okay? Some reactions, you could write a reaction for it, but it's not favorable for that reaction to happen, okay? So you have reactions that are unfavorable and reactions that are favorable. And how do we know when a reaction is going to be favorable or not? Meaning favorable, it will happen. Unfavorable, it will not happen. Well, energy determines whether a reaction will occur. I'm going to use the word spontaneously. If a reaction will occur spontaneously, that is a favorable reaction, okay? We'll say favorable. A spontaneous reaction, one that once you get it going, it'll just run to completion. You don't have to do anything else to it. It'll run on its own. That is a favorable reaction. All right, so and energy has everything to do with whether a reaction will happen or not. Now, I'm going to fill in these blanks down below, okay? Hang with me, and then we'll talk about them. I'm going to read this statement. If the products have less, and here's our word, potential energy, stored energy, than the reactants, the reaction will occur spontaneously. The reaction will be favorable, okay? It will happen. So do you think this reaction with the gold and the water up top, is this a spontaneous reaction? Is this a favorable reaction or unfavorable? What do y'all think? Gold and water reacting together. Does that sound like a favorable reaction or unfavorable? Right, unfavorable. Okay, Savannah said unfavorable in the chat. Because from an energy standpoint, it is not going to happen spontaneously. It's not going to be favorable. And we're going to really get into the first portion of this today, because this is a complex matter. Okay, there's not just one thing we can look at to define whether a reaction is favorable or not. Okay, we can't reduce it we can't simplify it to say if we just know this piece of information, then we know if the reaction will happen or not. There's three things that come together. Okay, so that's why another reason I think chapter 7 is kind of difficult, because now we're going to look at this from three angles, and when all three angles are understood and come together, then we can determine if a reaction is favorable or not. So the first portion of this, the first factor is called enthalpy. It's a very bizarre N. This is an N. N-T-H-A-L-P-Y, enthalpy. And that's the factor we're going to talk about with the rest of our time today. And then next week, we will get into this other term, entropy. And then we will also look at chemical reactions from a temperature standpoint. All right. So enthalpy, entropy, and temperature. These are three factors, and we cannot fully understand chemical reactions and whether they're favorable or unfavorable unless we understand all three terms and how they come together. So let's examine the first one, enthalpy. This maybe some of you, has anybody ever heard this word before, enthalpy? This is a brand new term for you. This is probably going to be a new term for a lot of people. So let's think about, before I just tell you the definition of it, I want to explain a few things. When you have a chemical reaction, I want you to think about what is happening. If I just draw a very simple one here, if I draw a double displacement between A and B and C and D, you recognize this. We know in a double displacement reaction, what's going to happen? Well, A and B are going to break apart. Okay, and then C and D are going to break apart. It should be an anion. Okay, so what happened here is we broke bonds. Okay, we're going to break these bonds, and we're going to rearrange our cations and anions, and we're going to form new products. And we said in a double displacement, we'll get A and D, and then we'll also get C and B. So all we did here is we rearranged bonds, and that's what this statement says. Reactions occur via the rearranging of bonds. Okay, you guys know, you remember from chapter 2 that we don't create new stuff, we don't destroy atoms, and we don't bring in new atoms. We just break bonds and rearrange the atoms and form new bonds, and that's how we get new products. So when we think about rearranging bonds, making them and breaking them, here's what you need to know. Breaking a bond requires energy. It requires an investment of energy. Okay, we have to pay those reactants some energy to break the bonds. Okay, and on the flip side, making bonds releases energy. Breaking bonds requires energy, and making bonds releases energy. If you've memorized anything today, memorize these two statements. So if we are looking at this chemical reaction up here, where I've written A and B makes, and C and D make AD and CB, which side do we have to invest energy on? The reactant side or the product side? Which side are you breaking bonds? Do you break them on the reactant or the product side? Caitlin says the reactant side. Jenna says reactants. That's correct. We break bonds on the reactant side. So over here, we're going to be on the eraser. Breaking bonds. And on the product side, we are making new bonds. All right. So because we've written that in, on the reactant side, this is where we invest energy on the reactant side, and on the product side, we release energy, okay? All right, any questions so far? So after we talk about making and breaking bonds, that kind of begs the question, well, how much energy are we talking? You know, and actually the answer varies widely, okay? How much energy do I need to break a bond? Well, it depends on a couple of things. It depends on the atoms in the bond, the identity of those atoms. That's going to determine how strong your bond is, okay? It's going to determine if you have a non-polar bond, a polar bond, an ionic bond. And sometimes different bonds are stronger and different bonds are weaker. And so it's going to require a different amount of energy for a strong bond than it would a weak bond, okay? And it also depends on the number of bonds. You know, you have atoms held together with a single bond, okay? Like a carbon-hydrogen bond are single bonds. But you can also have double or triple bonds, okay? So I've got some examples right down here for us to look at how different layers of bonds or numbers of bonds requires different amounts of energy. If we look at this nitrogen molecule, nitrogen, we know from studying Lewis structures, we found out that nitrogen, 2 atoms of nitrogen are held together with a triple bond. And so here's our triple bond, and what we see is it takes 226 kcal of energy. Remember, we studied units of energy. What are the 2 units of energy that we have? Calories and joules. So we're bringing those terms back. Don't forget how to relate calories and joules. On a side note, real quick, anybody remember the relationship between calories and joules? Let's just write it up here. How many calories equals how many joules? Jenna, take out the, there you go. 1 calorie is 4.184 joules. Don't forget that. Don't forget it, okay? Joules are smaller than calories. Calories are bigger. So I just want to remind you, that's what units we're dealing with here. Here we're talking about a kilocalorie. So it's a 226 kilocalories. If we have 1 mole of this nitrogen triple bond, nitrogen molecules, it would take 226 kcals of energy. That's a lot of energy to break all of those bonds and give us a mole of, or actually we'd have 2 moles here of nitrogen atoms, all right? But on the other hand, if you have a chlorine molecule, it's held together by a single bond. And look, it takes way less energy, only 58 kcals of energy per mole of chlorine-chlorine single bonds. So it takes 58 kcals of energy to break that chlorine, a mole of those chlorine molecules into chlorine atoms. Now, this amount of energy, the 226 kcals and 58 kcals, and it'll be different for every single molecule, or every single bond, I should say. We call that the bond dissociation energy. The amount of energy it takes to break a bond is called the bond dissociation energy. Okay, whenever you are disassociating, think about what it means to associate with something or someone. Okay, you're like, yeah, I know that person, or yeah, I'm a part of that program. To disassociate means to break apart, right? So the bond dissociation energy is the amount of energy it takes to break bonds. Okay. Well, and that's actually what we fill in down here. It's the bond, dissociation. Energy. All right, questions so far? I still haven't even defined enthalpy for you. We're just talking about how energy is relating to bond breaking and bond making. Any questions on that? Okay. So I'm going to scroll down just a little bit. Everybody got your blanks filled in. This right here, this table, this is going to be very, very, very handy for you next week on the dry lab. This table, this is in your textbook. It's table 7.1. You will use this table to do that dry lab. Now, a couple things I want to point out. What it gives you is it tells you there's 3 columns here of bonds. All different kinds of bonds. You've got carbon, carbon, single bonds, double bonds, all kinds here. And this is not all the kinds of bonds possible, but this is a good list of them. And then it tells you how much energy, the bond dissociation energy for that bond. And it gives you 2 numbers. So if we look at this very first one, carbon and hydrogen, it tells you the amount of the bond dissociation energy in kcals per mole, and it tells you the bond dissociation energy in kilojoules per mole. All right, so make sure as you're calculating these things, if you pick kcal, that you do kcal for every kind of bond. Don't switch back and forth and pick kilojoules for one bond and kcals for another bond, okay? If you're gonna do a problem, do it all in kilojoules or do it all in kilocalories, okay? And because if not, you'll get the wrong answer mathematically. Another thing I wanna point out is over here, you see one bond on this whole table that has a little asterisk by it. What does that mean? Well, the asterisk takes us down here to the bottom of the table. It says the carbon-oxygen double bond. This is a unique bond. The bond dissociation energies are usually these numbers, usually. But if that bond is in a CO2 molecule, which we know CO2 looks like this. If we're talking about the carbon-oxygen bonds in CO2, these double bonds, for some reason, they're different than any other carbon-oxygen double bond. They have a different number. So I just want to point those out. If you are calculating bond dissociation energies in a reaction and that reaction contains CO2, do not use these numbers for CO2. Use the ones down here that are listed for CO2, okay? Questions there? All right, let's continue. We're about to define enthalpy, but one more thing before we do that. We looked at these figures just a second ago. How much energy does it take to break apart molecules into atoms? And we said, okay, it takes a certain amount of energy. I also want you to know if we take those atoms and we reform the bond, if we make the bond, guess what? We're going to give off the same amount of energy, all right? So these 2 figures down here with the nitrogen and the chlorine atoms, coming together to form the bonds, this is the exact opposite of the figure up above. I'll call it figure 1 and figure 2. Figure 2 is the exact opposite of figure 1. Abby has a question. Does that mean that for the whole molecule of CO2 that it takes 191 kcal or, oh, good point. Yes, Abby, there are 2. Okay, here's 1 carbon-oxygen double bond. There's 2 carbon-oxygen double bonds. So yes, if you were calculating the bond dissociation energy for the entire molecule, you would have to take this number over here and multiply it by 2. Same idea for this one, times 2. Because there's 2 of that kind of bond, 2 double bonds in the molecule. Great question. We'll get into that a whole lot when we actually go about calculating these things. Okay. So all I want to point out is between figure 1 and 2, we have the exact reverse opposite thing happening here. In figure 1, you're breaking the bonds apart and you're forming the atoms. In figure 2, you're taking the atoms and you're forming the bonds. And the way energy is associated with these 2 things is opposites. For reaction 1, we're investing energy on the reactant side. We're putting in energy. And in figure 2, energy is a product. Okay, here energy is a reactant. Because remember, breaking bonds requires energy. Forming bonds or making bonds releases energy. When you're breaking bonds, energy is the reactant. When you're forming bonds, energy is the product. Okay. All right. This is all summed up too in the law of conservation of energy. Which says this: energy is neither created nor destroyed in chemical reactions, it's just transferred. okay? Just transferred. We just the same way when we make and break bonds and form new products, we don't create or destroy atoms, we just rearrange them. Same idea with energy. We don't destroy energy or create new energy, we just, the energy goes into different places and different forms. So our last blank here is the energy required to break a bond is the same as the energy released in making that bond. The same, or you could write equal to. Okay, so the energy required to break a bond, which is figure 1, it's the same as the amount of energy released when you make the same bond. Okay. Okay, now that we've had this preliminary discussion, let's actually define what enthalpy is. Enthalpy, and we abbreviate it with an H. I don't know why. That's just what we do. Enthalpy, H, is a measure of the energy stored in reactants or products. And let me ask you this, where are we storing the energy again? Where is energy stored in a reactant or a product? Anybody remember what kind of, I don't know if we directly said it, we've kind of talked around it. In the nucleus? It's not in the nucleus. Where is energy stored in reactants or products? Thank you, Kathleen. It's in the bonds, okay? That is where energy exists, okay? Energy stored, and it's stored in the bonds, okay? That's why we said when you break bonds, it requires energy. When you form bonds, it releases energy. And so we're going to learn how to calculate or measure enthalpy. And then we're also going to learn how to calculate a change in enthalpy, which we put in the Greek sign delta, delta H, as a reaction goes from reactants to products. So as you have your reactants and then you rearrange them and make your products, you're going to have a change in enthalpy across that chemical reaction. So we're going to learn how to calculate a change in enthalpy, and that is the difference between the energy needed for bond breaking and bond formation. All right, so we're actually going to now practice calculating a change in enthalpy. So let's look at this. We have this reaction right here. We have nitrogen gas and hydrogen gas coming together to make ammonia. I said ammonia is a really important molecule globally. We depend on it for all kinds of things. So let's look at what kind of bonds we have. If we're going to calculate a change in enthalpy, the first thing we have to do is we have to say, okay, what kind of bonds do I have in my reactants and in my products? Then we're going to go up to this table, find their bond dissociation energies, and then I'll show you how we put it all together and we calculate change in enthalpy. So the first thing we need to do, step 1, we're going to draw out Lewis structures. That's how we know what kind of bonds we have, right? So guess what? You cannot forget how to do. Draw Lewis structures, okay? So we know N2, guess what? I have it conveniently down here for us. N2 is a triple bond. Now how many, this is balanced already for us. Looks like it's balanced. How many nitrogen molecules do I have here? What's my coefficient? Just one, right? I just have one nitrogen molecule, so that means I just have one nitrogen triple bond, and it's associated with that amount of energy. All right, we'll come back to that. Let's move to the next reactant. I have 3 hydrogen molecules, so I want you to draw out 3 hydrogen molecules, their Lewis structures, right beneath. There they are. So how many hydrogen single bonds do we have here? We have 3, right? Now let's draw out a molecule of NH3. And guess what? We have 2 of them, so we need to draw out 2. So we have nitrogen, 3 hydrogens, and it gets a lone pair. And then I'm going to draw out another one. Nitrogen, 3 hydrogens, and a lone pair. Okay. So I have all the molecules drawn out now, all their Lewis structures. And now what we need to do to calculate the change in enthalpy here is we need to add up the amount of energy that is in these bonds on the reactant side and on the product side. Okay? Now for the first one, there's no calculating. We just have one nitrogen triple bond. So it would be 1 times 226 kcal per mole. For our second molecule, hydrogen, we have 3 hydrogen single bonds. So here is the bond dissociation energy. If you go up to the table, I believe it would be the same number, 104 kcal per mole. But we're going to multiply that by 3 because that's only for 1 hydrogen single bond. We have 3 in this reaction. So we're going to do 3 times 104 kcal per mole. So we'll add these two together. Can somebody tell me what's the total amount of energy that we have to invest on the reactant side to break all of these bonds? Aaliyah says 538. I'm going to pull this up just a bit. 538. Okay, thank you, Aaliyah. 538 kcal per mole. That is how much energy total we would have to put in to break that nitrogen triple bond and all 3 hydrogen single bonds. And then now the atoms are free to arrange and reform new bonds to make our product. So how many bonds do we have? Well, let me ask a different question. What kind of bond do we have on our product side? What kind of bond do y'all see over here? In the molecule of NH3, they're both identical. What kind of bond? A nitrogen-hydrogen single bond, right? And how many do we have total across both molecules? 6. And do we have any other kind of bond? That's the only kind of bond we have, right? So all we're going to do is we're going to come get the number, the bond dissociation energy for the nitrogen-hydrogen single bond. It's 93, and we will do 6 times 93 kcal per mole. All right, so somebody can tell me, once you do that in your calculator, Aaliyah, 558 kcal. That adds up to 558 kcal per mole. So we needed 538 kilocalories of energy per mole of all these bonds, and we're going to release 558 kcal of energy per mole of these nitrogen-hydrogen single bonds. All right. Now, looking at this, the change in enthalpy, delta H, is the enthalpy, which we abbreviate with an H, of the reactants minus the enthalpy of the products. I'm just writing reactants and products as little subscript words so you know that H here is associating with a different side of the reaction. This is how we calculate delta H. We take the enthalpy of the reactants and we subtract off the enthalpy of the products. So can someone tell me what is our delta H for this particular reaction? So you do 500, enthalpy of the reactants here is going to be 538 kcal per mole. Don't forget the per mole, minus 558 kcal per mole. And Kathleen and Allison, they all say negative 20 kcal per mole. And that is correct. Let me move this up a bit. So ultimately what that equals is negative 20 kcal per mole. That is our delta H. Okay, so we just learned how to calculate a change in enthalpy. Now, sure, you can calculate the number, but what in the world does this mean, right? That's what we need to, that's what I want you to understand. What does this mean? Let me look at the next slide. This is actually what we just did, okay? We calculated the enthalpy of the reactants and the enthalpy of the products, and then we put it all together. What we're going to do is we're about to classify this reaction as exothermic or endothermic based on our delta H. So what this means is that overall energy was given off, okay? Energy was released. So if we did this reaction in a test tube, what would happen to the test tube if I'm doing this reaction and overall energy is given off? How would the test tube feel to me? Would the test tube get hot or would it get cold? Okay, it would feel hot. This is what I want you to grasp from this stuff. This reaction is giving off energy overall. And we calculate that and we determine that by calculating the enthalpy of the reactants and the enthalpy of the products and finding the difference. So this test tube would feel hot. Okay? All right, so we actually already did this. We learned how to solve. These are just the same definitions we did right up here on slide 1, so don't worry about those blanks. We just learned how to solve for delta H on the slide above. This is just kind of a summary of what we calculated. Now let's fill in the blanks down here. When overall heat is, what was my, I forgot what my blank was for this. Oh, when overall heat is released, which is what we see happening in this reaction, delta H is negative. Okay, when overall heat is released, delta H will be negative, and that's what we found in this reaction because our enthalpy of our products was bigger, and when you subtract a bigger number, you get an overall negative answer. If overall heat is absorbed in the reaction, guess what? Your delta H will be the opposite, it'll be positive. When overall heat is released, delta H is negative. If overall heat is absorbed in the reaction, delta H is positive. Now, what does this mean? That means here, with the first statement, that the enthalpy of the products had to have been a bigger number. Here, your enthalpy of your products is a larger to bigger number. If heat is absorbed, that means enthalpy of the reactants was a bigger number. Aaliyah, help me clarify. Is that because it is negative? What do you mean? Is what because what is negative?
When it gives off heat, is that how we know that it's releasing energy?
Yeah, if your delta H is negative, then that means the reaction itself, if you're viewing it from the standpoint of the reaction, it is giving off energy. And we are not the reaction, we are the surroundings, okay? So if that reaction is going on in that test tube and it's giving off heat, your delta H is negative. Does that answer your question?
Yes, ma'am.
Okay, good. Any other questions about this? This is definitely technical stuff we're doing. And this math is not hard, but it is technical because you have to very carefully count the number of bonds you have. If you get off by one bond, you're going to miss the whole problem, right? So you have to remember how to accurately draw your Lewis structures, and then you have to be able to count bonds and kinds of bonds, and then add everything up correctly. All right, let's do another reaction here. We're gonna do another one. In this reaction, we have nitrogen gas and oxygen gas, and they're coming together to make nitrogen oxide, nitrogen monoxide. So we actually don't have to draw anything out this time because we have the numbers given for us. The only thing we need to make sure we do is multiply by the right number in case there's more than one kind of molecule or more than one molecule. We have to look at our subscripts essentially, or sorry, not our subscripts, we have to look at our coefficients. So what this says, if it's balanced, and it looks like it's balanced, is that one nitrogen molecule plus one oxygen molecule is going to give us 2 nitrogen monoxide molecules. So we would do these numbers times 1, and this one needs to be times 2. And then on the reactant side, we have to add everything up. So we'll do 226 plus 119. So because it's multiplied by 1, we know that doesn't change the number. So I'm just going to ultimately write a little plus sign between these numbers. So how much heat input, how much heat or energy do we have to put into the reaction to break our nitrogen and oxygen bonds so that the atoms can rearrange and give us our products? And Aaliyah says 345 kcal per mole. All right. Now, what is our heat output? When we make a molecule of nitrogen monoxide, we make that bond, we're going to give off 151 kcals, but we're making 2 of those molecules. So we multiply that number by 2. And so what is our heat output? Jenna says it is 302 kcal per mole. So what is our delta H here? Delta H is 345 minus 302. (345 kcal per mole minus 302 kcal per mole, and you should get it is a positive 43 kcal per mole. All right, positive 43 kcal per mole. So here our delta H is different. In the first reaction, it was negative. Now it's positive. And so what that means is overall heat was absorbed, and we got a positive delta H. Yes, Aaliyah, if we were doing this in a test tube, what would happen to that test tube? For us, since we're the surroundings and overall the reaction is absorbing heat, that means there's going to be an absence of heat in the surroundings. And what we would feel is that the test tube would get cold. If there's an absence of heat in something we're touching, because that heat is being absorbed literally into the bonds of the reaction, and they're storing it in the bonds, then we feel the absence of heat as a coldness, all right? Also, if I had to write energy into this equation, overall, looking at my delta H, should I write it in as a reactant or a product? What do y'all think? Jenna says a reactant. Anybody disagree? I agree with Jenna. Overall, we have more energy over here on the reactant side. Okay, that's a higher number. So I'm going to take this excess energy, the difference, which was 43, and you can write that in as energy plus your reactants. So I could say energy plus, or I could literally just write the number in, 43 kcal per mole plus my reactants, okay? So if I give you a reaction and I say, here's your delta H, write energy in as a reactant or a product. If your delta H is positive, and that means your heat input was larger. Your enthalpy of your reactants was larger. So you're going to write energy, the energy term, the excess amount, okay, your delta H, as a reactant. You're writing it on the reactant side. Now, if we go up here above, we saw that our delta H was negative 20 kcal per mole for this reaction, okay, the nitrogen and the hydrogen making ammonia. So because delta H is negative, what that meant, what we found, was that our enthalpy of our products, it was a larger number than our enthalpy of the reactants. So this time we're going to, because it's negative, we're going to write energy, so we would, as a product. So we put plus energy. Or you could literally write plus 20 kcal. Now, here's what I don't want to be confusing. Yes, this delta H is negative, which to us indicates overall that energy is given off. But when you write it into the reaction, you drop the negative and you just write the absolute value of that energy amount. The fact that you're writing it in on the product side indicates that your delta H is negative, okay? The fact that you're writing it in on the product side indicates that your delta H is negative. So if you write it as delta H, it's negative, but when you write it into the actual equation as a product, you can just write the absolute value. Questions there? So what we found here is that 43 kcal per mole, more energy was needed for bond breaking than what was released when we formed our bonds on the product side. Therefore, we can say this statement, overall heat input is needed. And that's why we write energy in as a reactant. I get ahead of myself. We already calculated what our delta H was. Okay. But I'll just rewrite it down here. It was 43 kcal per mole. All right. These are just some summary statements. Hopefully I've said this enough now that you're ready for me to move on. When heat is released, delta H is negative. When heat is absorbed in the reaction, delta H is positive. Okay. Oh, I put that table back in here in case we needed it, but I don't think we did. But we might for, okay. All right. So now I'm going to introduce two more terms. You ready for two more vocabulary terms? So we're going to enthalpy today. Here's the two reactions we just calculated for. All right, and here were the numbers we found for our delta H's. So if heat is released and delta H is negative, we call this kind of a reaction. Anybody know what kind of reaction we call it? Anybody want to guess what term? Yeah, that's right, Jenna, exothermic. Okay, maybe you've heard that word before. Who's heard of the term exothermic before? Anybody heard of that term? Okay. It's an exothermic reaction. Thank you, Allison. If heat is absorbed and delta H is positive, then the reaction is, guess what? The opposite of exothermic is, anybody know? Yes, endothermic. Exothermic reactions give off heat. Endothermic reactions absorb heat. Okay. Exothermic reactions we feel. Okay, I'm just gonna write a statement here. The test tube would get hot. We would feel the release of heat. If we were doing an endothermic reaction in a test tube, the test tube would get cold. All right, so I have our first poll question. We have about 10 minutes left. This is good. We may not get through all of these slides, but we'll get plenty of practice calculating this stuff next week. I'm gonna run a poll question. Let me find it. Here it is, launch poll. Okay, so I want you to look at this slide right here, reactions 1, 2, 3, and 4. And I have a poll question that corresponds to each one. I just want you to tell me if it's exothermic or endothermic for each one. So take a second, look at them, select your answers. You'll have to select your answer for all 4 before you can submit it. About half of you voted. All right, 92%. Anybody else want to vote? Got 2 more people? Okay, I'm gonna end the poll. Let's look at what you guys said. Share results. So looking at the first one, everybody said this is exothermic. Okay, so heat is a product. So yes, definitely exothermic. Good job, all right. Number 2, 84% said endothermic and 16% said exothermic. Here, heat is a reactant. And if heat is a reactant, then overall, your delta H, like what we saw in this reaction up here, your delta H was positive. So that means, how did we write heat in? We go up to this reaction. With this reaction, we wrote the energy, the heat term in as a reactant. So if heat's a reactant, that's because your delta H is positive. And that kind of reaction we said is endothermic. All right, if heat is a reactant, that is an endothermic reaction. Number 3, delta H is negative and 80%, oh sorry, number 3. 80% said it is exothermic, and you are correct. The 80% is correct. This is exothermic. If delta H is negative, then heat is a product. Overall heat is given off, which is an exothermic reaction. And then the bottom one, if you notice, 3 and 4 are just opposites of each other. So because of that, delta H is same value but opposite sign. It's a positive 503 kcal per mole. So it's the opposite kind of reaction. It's endothermic. Okay, any questions there? All right. If we don't get to the last 2 slides here, that is okay. We can do that, but I really want to get through this slide in our remaining few minutes. So we'll just do this last slide and then we'll be done. We have a reaction here. CH4 plus O2 makes CO2 and water. Guess what? What kind of reaction is this? Anybody classify this? Well, okay, yeah, I'm talking about like single, double displacement, combination, combustion. Abby says combustion. Yeah, this is a combustion reaction. Now, what do you know about combustion reactions? Do they give off heat or absorb heat? They're usually, you can observe a combustion reaction. It's like an explosion, right? So it's going to give off heat. So it makes sense that in a combustion reaction, your delta H is negative. Heat is a product. And if your delta H is negative and heat is a product, is this exothermic or endothermic? That's question number 1. What do y'all think? Is this combustion reaction exothermic or endothermic? Delta H is negative. Kaylin says exo. That's correct. This is exothermic. All right, now we want to know, look at the reaction 2. It is balanced, okay? We have our coefficients in. I have a coefficient of 2 in front of oxygen, in front of water. So we've got 1 carbon on each side, 4 hydrogens on each side, and 4 oxygen atoms on each side. So this is balanced. Now, what if we do the reaction with only a third of amount of our carbohydrate, which is like the fuel in a combustion reaction, okay? If we did it with a third of the amount of fuel, 0.35 moles of CH4 instead of, how much does this reaction say we have? 1. There's an understood 1 here. So if we did it with, if we did it with 3.35 mole instead of 1, how much heat would be released? This is a conversion problem, okay? We need a relationship or conversion factor to do this problem. So we are about to write a brand new style of conversion factor where we relate a reactant or a product to the amount of energy. What the reaction up here tells us is that for every 1 mole of CH4, we will produce negative 213 kcal per mole of energy. We can write that relationship by looking at our coefficients in the balanced reaction. I could write that for any of the reactants or products, okay? We could say for 2 moles of O2, same thing. We'll produce negative 213 kcal per mole, okay? When you figure out what your delta H is for that reaction, you can go in and you can start writing these kinds of relationships. So I'm going to need this relationship right up here to do this first problem. So I can write it as a conversion factor with 1 on top and 1 on the bottom. I'll just say for every 1 mole of CH4, it's negative 213 kcal per mole of energy, okay? So how much heat is going to be released if we just do it with 0.35 mole of CH4? So we're going to start with the number given, 0.35 mole of CH4. And we want to convert to units of heat. What are our units of heat? Heat is energy. So what are our units of energy? I actually don't think I even need to write the per mole part in this. If we just want units of energy, then we just are wanting the kcals or the kilojoules. Okay? So you can leave off the per mole part here. We just want units of heat or energy. All right. So we're going to use this relationship. How should I plug it in? This way or should I flip it? I want to cancel out moles of CH4 and I want to convert to units of kcals, which is units of heat here. So I'm going to flip it. I'm going to plug in for every, I know for every 1 mole of CH4, the reaction produces negative 213 kcal. So because this reaction is related to this delta H, I can write these kinds of relationships and I can use them as conversion factors. Guess what? I'm probably going to have you do on the quiz next Tuesday. Cough, cough. Okay. So we do 0.35 times negative 213 divided by 1, and Jenna says she got negative 74.55. And I'm just going to write units of kcal because that is units of heat. Okay. All right. So there we are taking a number of moles and converting to heat. Guess what we're doing on the bottom one? We're taking, what if we now only have 7.5 grams of CH4? How much heat is released? Can we do that? We're going to do it the exact same way for the problem we just did, except for there's an added step. First, before we can just throw in that conversion factor, we have to take this number of grams and convert to moles. So to do that, how do you go from grams to moles? That's what we did all chapter 6 on exam 2. We're going to need a molar mass of CH4. So the molar mass of CH4 is equal to carbon. We just have 1 carbon, so that's 12.011. And we have 4 hydrogens, so we'll do 4 times 1.01. So we'll do 12.011 plus 4.04, and you should get, I really don't have space down here, but 16.051 gram per mole. That is my molar mass. So I'm literally going to take 7.5 grams, and I'm just going to continue my problem. I'm going to plug in 16.051 grams here for every 1 mole. All I'm doing is I'm taking grams of CH4 and converting to moles before I convert to units of heat or energy. So first I calculated the molar mass of CH4. I used the molar mass to convert to moles of CH4. If you notice, grams of CH4 cancel. Okay, bye Olivia, head to class. We got 1 minute, I'm almost done. And then lastly, I'm literally going to plug in the same conversion factor we wrote right here, because I want to cancel moles of CH4 and convert to kcals. Okay, so how do I cancel moles of CH4 and convert to kcals? Exactly the same way we did in the previous problem. For every 1 mole of CH4, it was negative 213 kcals of energy. And how did we get this relationship? Well, we looked at our balanced chemical reaction. We said in the balanced reaction, we needed 1 mole, and if everything else goes as written, we will get negative 213 kcal. So we just took those numbers and we made a relationship from them. So now you'll do 7.5 divided by 16.051, and you'll multiply by negative 213, and what do we get? Moles of CH4 cancel. Abby says she got negative 99.527, and the units on that are kcals. Okay. All right, so we'll stop there today because we are past a minute past time. I bet your brains are, I know mine is. Told you chapter 7 was dense, but we can do it. If there are any questions, I will stick around. I'm going to upload the chapter